All right, we are on gradients 2. And what does it look like we're doing? Computing directional derivatives. And pretty much that's it. Oh, and just a word of warning. Number 2, when I did the problem on the video, I did it wrong. But then I corrected it on the written thing. So if you just look at the written solution, then it's correct. But if you watch the video, it's wrong. Okay, so how can we compute a directional derivative? Well, you just look at the notes right here. All you have to do is take the gradient and then dot it with a unit vector that's in the direction that they want. So like if you look at problem number 1, it says compute the directional derivative at the given point in the direction indicated. It's quite simple. So why don't we make up a function then? What's the first one? Elliptic paraboloid? Why don't we just do a regular paraboloid then? X squared plus y squared. Of course, let's look at what the graph looks like. So isn't it going to look something like this? Right? Okay, what would be a point on this graph? 1, 2, no, let's not do 0, 0, 0. How about like 1, 2, 5? Okay, so 1, 2, 5 might be up here. Here is the point 1, 2, 5. And let us compute the directional derivative in the direction indicated. Well, what direction do we want to look at then? Because the point has to be going in some direction.
0, 0, 0.
No, not 0, 0, 0. Look, can we even make up numbers?
3, 4, 5.
No. Well, if you look at it, it's going to be only in 2 dimensions there. You only have 2 dimensions. So, how about 2, negative 1 then? So compute the directional derivative. So first of all, you compute the gradient. The gradient of f is what? What's the partial with respect to x? 2x. What's the partial with respect to y? 2y. Oh, shoot. And at this point, what is the gradient? If you plug in 1 for x and 2 for y, you get 2, 4. And then you simply dot that with a unit vector that's pointing in the indicated direction. So the length of this vector is what? Root 5. So therefore, what is the unit vector that points in that direction? 2 over root 5, comma, negative 1 over root 5. If you compute the dot product of this, that is the directional derivative.
How come like the vector, there's no z component, but the point has?
Oh, well, that's the next thing we're going to talk about here. Well, yeah, just wait till the next problem, okay? So how do you compute this? What? 4 over root 5 minus 4. Oh, yeah, it is 0. It's 0. The directional derivative is 0. Question.
You want to say it's going to be a little bit.
Say that again?
You want to say it's going to be a little bit.
Okay, why don't you tell him that his grade will be a little low? Wait, how did he tell you that?
I just texted you. I just saw his text.
Okay, so all you're doing in number 1 and number 2 is computing directional derivatives. It's just computation. Okay, but the interesting thing comes from this though. A differentiable function f increases most rapidly in the direction of the gradient.
Easier.
So where's the note? Don't you guys still get notes?
Oh, then he's getting enough money too.
What?
I was doing like.
Just sit down, okay? Just sit down.
Yeah, he told him. Okay.
And you wanna know what I told him?
What did I tell him?
So that's okay, you can watch the video. Anyway, it says, a differentiable function f increases most rapidly in the direction of the gradient and decreases most rapidly in the opposite direction. So like if you are on a surface, like what is the path of steepest descent or steepest ascent? Well, it increases most rapidly in the direction of the gradient. So like for this paraboloid right here, so here is the point 125. What is the path of steepest ascent? Okay, first of all, okay, let's dissect the words. Ascent, what does that mean?
Going up.
Going up, okay, and then steepest. So like, what direction do you have to travel to go up the steepest path? Or what direction do you have to travel to take the steepest descent? Yeah, I know up, but exactly how up? No, but you have to stay on the surface. You have to be on the surface. Well, anyway, it says it's in the direction of the gradient. Now, what is the value of the gradient at this point? Well, we already computed, right? Isn't it 2, 4? Didn't we compute the value of the gradient at that point? This is the path of steepest descent. Now, you might be thinking, well, why is it a 2-dimensional vector? Shouldn't it be 3? Well, no, it's only 2 because, here, I think the easiest way to think about this is look at the level curves. Remember the level curves, we talked about that? So when z is equal to 0, this is like z, huh? When z is equal to 0, what is the cross section? Yeah, point at the origin, right? Wasn't Song talking about this last time too? Okay, what happens when z is 1? In other words, 1 unit above the xy plane, what is the intersection of the paraboloid and the plane z equal 1? It's a circle, x squared plus y squared equal 1. So it's a circle of radius 1. So that's a level curve when z is 1. So you put z equal 1. Okay, what would happen if z is equal to 4? You get a circle of radius 2. So you get 2, 2, 2, 2. So it looks like this. So this is when z is equal to 4. What about when z is equal to 9? You get a circle of radius 3. It looks like this. These are called level curves. Okay, but see the thing is, you gotta think of this 3-dimensionally, right? You're going up like this. But then you're only looking at it like this. So if you are at the point 1, 2, 5, where would that be? 1, and where's 2? You go 1 this way. What is 2? Is it 2 up here? And then 5 is up here though, right, somewhere. But then it doesn't matter because you're looking at just the level curves in a plane like this. So at this point, the path of steepest ascent is going to be this vector here. It has an x component of 2 and a y component of, so it's like this. You go 2 to the right and 4 to the up. It's going to look like that.
I use 3.
Anyway, doesn't it kind of make sense? Because look, isn't it emanating away from the origin?
Yes.
Right? Because this was a 1 to 2 ratio, right? So if you just continue to write 2 and 4 is the same ratio, right?
Is it always like that?
Well, that's because the cross sections are circles, right? But like the one you have in number 1A, it's an elliptic paraboloid. So it's not, right? It's not totally symmetric, right? You know what I mean? So it's not going to be like emanating directly away from the origin. And then what is the path of steepest descent? It would be the opposite of this. Then it would be -2, -4. So it would be a vector going like this, right? If you reduce the vector down. Doesn't that kind of make sense? So that's one way to look at it. Another way is, if you think about it 3-dimensionally, okay, here's the point right here. What is the path of steepest descent? 2, 4. So in other words, if you drop this point down onto the xy plane, And then you draw this vector, 2 comma 4. Isn't it gonna look like this? Let's see, 2, 4. Like that? Right? You take this is the same vector except you keep it in the xy plane. So remember, you're gonna be traveling on the surface. So you're here. What is the path of steepest ascent? Well, you're standing here. Okay, so where shall we put the origin? Okay, here's the origin right here. Right there. Okay, so I'm at the point 1, 2, 5. Okay, so pretend I'm at the point 1, 2, 5 now. And I have to travel on the surface of this paraboloid. What is the path of steepest ascent? I need to follow the vector 2, comma 4. So like on the ground, if I go 2 to the right and 4 that way, I have to walk in this direction. But you're going to be on the paraboloid.
It's 38 no room they gave up.
We're talking about,
Where did that come from?
we're talking about the Giants game.
I know, well, I was listening to ESPN
Oh, no,
radio.
not the Giants, the 49ers. No, the Bucks.
Oh, I don't even know how that thing came on. Why are we even looking at it?
Oh, we're talking about Aaron Rodgers.
Where are we? Oh, here, we're here. Oh my goodness. Okay, so now do you get it? Why it's only you only look at the x and the y components?
What does the 0 mean again?
The directional derivative, I guess, is 0. That means at that point, then there will be no slope. That means the function is neither increasing or decreasing in that direction. So anyway, that's what a directional derivative gives you. Anyway, it's pretty easy. You just gotta compute it. So like this test, I'm guessing we'll have no notes again. No, there's hardly any formulas. Like that formula, that's okay. So that's the chain rule right there. But that's no different from the chain rule we saw in 2 dimensions, right?
Find the green.
We don't need the formula for the chain rule. If you need a formula for the chain rule, then what? Just go home and cook rice, right? Okay, let's do an example covering number 4 then. Use the chain rule. Using the chain rule, find the rate of change of a function of 3 variables. Okay, let me erase this. Okay, give me a function of 3 variables. That's similar to tonight's homework. What do they have there? X squared y plus z cosine x.
Find
How about,
Y squared
no, come, think of something unique. How about like xy plus xz plus yz? Do you guys ever wonder what these graphs look like?
Yes.
No, you guys, okay, you guys have your regular HP prime, right? Okay, try graph it. Do you have the 3-dimensional grapher, 3D grapher? That should be one of the apps. You can't use the one on your iPad, you have to have the actual, the iPad one is the light one. Where's your HP prime? Oh no, it's just one thing after another, so. Wait, I'm gonna revise the letter right now.
No, no, I brought it to ACT and then I lost it. What? You lost your HP prime? Yeah.
Oh yeah, I lost something too.
No.
Respect.
Oh.
Oh.
They're hard,
No.
they're still screwed.
What? Yeah, we're gonna go to Desmos.
Oh. Wait, so it doesn't work on your iPad, but it works on the computer?
No, we're doing Desmos. I was talking about the HP prime. Okay, who has the regular HP prime calculator with them? Does it have a 3D grapher?
Yeah.
Yeah.
There's 3.
Oh gosh, here we go. Oh my goodness. Where's is it called Desmos.com? There you go. Okay, do we? I wonder if Desmos, well, let's just try. X times Y plus
for like a value of Z.
X times Z, because that's not Z, plus y times z.
You can go to like GeoGebra, I think. Wait, how do you graphs?
Okay, here, just 3D grapher. I'm pretty sure I did this on Desmos before. GeoGebra. Okay, we'll do GeoGebra then. Ooh, I like it already. X times y. Oh! What graph is that? Redeem yourself, Sam.
XY?
No, but what is the shape? Look at it.
시원한. hyperbola with one.
Hyperbolic paraboloid right there. It's right there. Oh my god. Plus x times z. Good thing we're getting this on film, man. Plus y times z.
Don't you always set it equal to something? Like that, because the rest of
Oh, wait a minute. This is a 4-dimensional graph, yeah?
Yeah.
Okay, never mind. We don't even have a 4-dimensional grapher. Oh, well, there you go. Okay, I guess we can't do that. Never mind. Anyway, there is a 3D grapher on your HP Prime. That was the point of all of this. But you can't use the one on your iPad because that's the light version. Okay, using the chain rule on this, find the rate of change of f along the curve. Okay, somebody give me a curve. What's a good, what curve is that? Let's just do the helix then. How about cosine t, sine t, t? Isn't that just the helix? Okay, and do we need to, no, we'll just compute the rate of change. So, according to the chain rule, look at the thing. So du what are we doing? dt is equal to du dx times dx dt plus du dy, this is a u now, times dy dt plus du dz times dz dt. Right? That's the chain rule, extended to higher dimensions. Okay, so let's do this. What is du dx? This is, and by the way, if you didn't know, this is u. So what is du dx? Song, redeem yourself again.
Y plus z.
Times dx dt. And remember, this is like x, y, and z parametric equations. Song?
Minus sine t.
See, so easy. Okay, next one. Hong, du dy.
X plus C cosine T.
And then learner.
X plus y.
Times 1. And there you go. And do you have to compute it at a certain value? What does it say? No, we don't. And then of course, what if you have to change, look at the answers. Are the answers in terms of t?
Yeah.
Let me look. Yeah. Okay, so how can I change the answers all in terms of t? Well, look, this is x, y, and z. Just plug in. So you're gonna get, what is that? Sine t plus t times negative sine t plus x cosine t plus t times cosine t plus cosine t plus sine t times 1. And I don't know, what kind of simplifying do you see here? Not that much, yeah. I think some of the ones on tonight, somewhere in the simplifying is pretty good. This one is really not. Okay, I think that's pretty much it. And then number 5 is just an application of the chain rule. A word problem, but I think you guys can handle that. So we're not, even tonight's homework is just basically computation, and even I'm looking at the preview of gradients 3. What we're gonna do is write the equation of the tangent plane on a surface. That's really easy. So we're not gonna get into the heavy duty stuff until gradients 4. We're gonna have to do a lot of algebra. In fact, there's one problem, because I made the video for gradients 5 and 6 this weekend. Gradients 5, the last problem on the homework, it usually takes us the whole board to do.
Oh, yeah.
So I didn't do it, I just said, I wrote on the thing, just watch the video. Because it takes the whole board. Remember, and every year we do it differently too. So, I don't know, we'll just find out which path we take when we actually do that problem. It's a doozy. Okay, any questions on this? Directional derivative, easy, yeah? Okay, we're done. Play one game and go to lunch?
Sure.
Okay. Why are we whispering?